Okay, welcome back to the second half of lecture 28. This is talk about Karnaugh maps and where we use them to simplify logical expressions. Now, you don't have to use Karnaugh maps to simplify logical expressions. Some of you will have seen this content in ENGR101 where there are Boolean, algebra, logic operations that allow you to simplify these things down, and those are the mathematically rigorous and correct way of doing this. But like with many things in engineering, there are also little tricks and tips to help you along the way, and Karnaugh maps are simply one of those for simplifying logical expressions. It shouldn't replace your knowledge of Boolean algebra, but it should give you a simple trick way of checking your answers or calculating your logical expressions in a slightly different way. So in the first half of this lecture, I gave you that hideous expression that you can see up the top with 3 different inputs from a bunch of different terms, and I told you to draw me a logic circuit from that. And what we can establish is that if we simplify the expression first, it makes drawing and then physically making that logic circuit a lot more simple, which is why we do this kind of simplification. So what I've got down on the bottom of the slide there is an example of something called a Karnaugh map. And there's not just one way of doing them, there's lots of ways of doing them. So I'm going to show you 2 in this lecture. This first one here is a little bit more clear, but you can think of it like a truth table wrapped around on itself. So all I'm trying to do with a map is I'm trying to list every possible combination of input for A, B, and C, and see which one of those correspond to a particular output. So here I've got my Y, which is my output, and I've got my A's down here with a 0 and a 1, and my BC's up here with a 0, 0, 0, 1, 1, 1, and 1, 0, like this. So let me explain what this map is actually showing you. There we go. So all I'm saying here is that for, let's say, this line along here, this line here is saying what happens if A is false? What happens if A is 0? And this one here is saying what happens if A is true. So this column here is saying what happens if A is 0 and B and C are 0. So if A is false and B and C are false, that's what goes in there. What happens if A is true and B and C are false? That goes there. This column here, for example, because it's got 2 1s, it means B and C are both true. So that line there, because it's got a 0 for A, that means what happens if A is false and B and C are true. This one down here is what happens if A is true and B and C are also true. So that list of terms that you can see up the top, the Y equals A, not B, not C, or not A, B, or C, or not A, B, and not C, running out of room, or A, B, not C. When I have an expression like that, all I'm saying is that each one of these terms corresponds to one and only one location on this map. So which term corresponds to which place? It's pretty simple. Let's have a look at this first term. A, not B, not C. When is that term alone, just this one here, when is that finally going to output 1? When is A and not B and not C true? Well, that's going to return true when A is 1, B is 0, and C is 0. Why? Because the not here, that turns a C from a 0 into a 1. The B there turns the 0 there, the not there turns B from 0 into a 1, and the A is already 1. So I go looking for that term. So my A has to be 1, and my B and C both have to be 0. That means that term there. And once I've found the correct map location for each term, I just put a little 1 in the box to signify, yes, there is a term that exists there. And then once I've done that term, I move on to this next one. So that one's done. Not A and B and C. So if it's not A, that means it's going to be along this top line here, alright? Because I'm looking for 0, 1, 1. 0, 1, 1 is that term there. For this third term here, I've got not A, B, and not C. That corresponds to 0, 1, 0. So I look for 0, 1, 0. That term there. And then finally A and B and not C. So this is equivalent to 1, 1, and 0. So I look for my 1, I look for my 1 and my 0. That term there. Okay. So I've populated my Karnaugh map with this whole set of terms here. And my next step is to use that to simplify things down. But before I do that, I'm going to show you one other way of writing Karnaugh maps, because the other way of writing them for me makes much more sense than this way I showed you. The reason I'm showing this to you is that I want you to see how the Boolean actual combinations work underneath this. But because we're using this as a tool for simplification, it's actually much easier to just draw the table like this. So what you'll notice is that the table in this form has exactly the same number of rows and columns, but instead of writing a 0 or 1, I write an A and a not A down that side. Okay, and here I have B and C, then I have B and not C, then I have not B and not C, and then I have B and, sorry, not B and C. Here we go. Exactly the same table, and I'm going to fill it in exactly the same way, and I'll just take you through it step by step so it's really clear what I'm doing at each step. Now I don't need to bother about that conversion to a 0 and 1. I'm just looking for the points on this map that correspond to each term here. So let's start with this term. I'm looking for an A, a not B, and a not C. Well, as it starts with an A, I have to look along this line, and a not B and not C, that corresponds to that column there. Right? Not A, B, and C. Not A, B, and C. That corresponds to that term there. Not A, B, and not C. Not A down the bottom. B and not C corresponds to that one there. And then A and B and not C, that corresponds to that term there. Now, the eagle-eyed amongst you will have noticed that I did something slightly subtle there, because this Karnaugh map doesn't actually look the same as the last one I had. The last one I had looks slightly different, and that's because of the order of these columns along here. The order of those columns matters. Okay? Your usual instinct when you're doing this is probably to write them out in a combination like you would for binary numbers, which would be like 0, 0, 0, 1, 1, 0, 1, 1. Don't do that for this. Okay? The important thing is that as I go across the columns or down the rows, because I can actually make a 4x4 Karnaugh map if I have 4 inputs, is that as I move across the columns, I can only change one thing at a time. So note, as I change from here to here, I change a C to a not C, and that's all I can do. I can't change my B at the same time. From here to here, I leave the C the same, but I change the B, and from here to here, I leave the not B the same, but I change the C. That's fine. If, however, you switch the order of those two terms, so imagine, let me write this up just to be super clear. So if this one here was not B and C, right? See how I've now changed both the B and the C by jumping across one column. That will cause my Karnaugh map to screw up and will cause my final expression to end up being wrong. So this one here needs to be not B and not C, and therefore this one here has to be not B and C, okay, which corresponds to our original map. Sorry, I've got one of those earlier ones wrong, so let's just check that again. A, not B, and not C, that's that one. Not A, B, and C, not A, B, and C. Not A, B, and not C, which is that one. And A and B and not C. A and B and not C. A, B, and not C. No, that is correct. Sorry, got myself confused because of that C there. Right, so now it's filled in. You can see an example of me filling this in step by term here. It's going what I'm doing. And so the final step, now I filled in my map, is I group the terms, and the fewer groups I have, the fewer terms I will have in my final expression. So what I mean by a group? By a group, in a Karnaugh map, it's a bit like playing Connect 4, but you can only go vertically or horizontally, and it's not Connect 4, it's Connect 1, 2, or 4. So what I'm looking at is I'm trying to draw groups around that either horizontally or vertically. So what you can see here is that there's two different ways of grouping these terms. I can either draw a group like that and a group like that, or if I use a different color, I could draw a group like that a group there, and a group there. So I will show you how to go through and actually do this for both groupings. But while we're here, notice that the black groupings, I have two circles, two groups. That means I'm going to have two terms in my final expression. The green ones, right? There are three circles, which means I'll have three terms in my final expression. While those two expressions, they'll be logically equivalent, right? They will output exactly the same thing. I would say the black one will be simpler than the green one, just because it has two terms rather than three. So how do I get those terms? Look at the black groups at the moment. So here's my output expression. When I'm looking at one group, I'm really asking the question, what doesn't change between these two terms? So this term here is A and B and not C. This term here is A and not B and C. What you can see there is that the A and the not C are the same for both terms. Okay? The B is not. The B changes between a B and a not B. And why is that important? That's the same as saying the value of B does not matter for this group. It doesn't matter whether it's B or not B. The A and the not C are the only things that matter. So those are the only things that get carried on to my final expression. So my term from that group there becomes A and not C, because the B doesn't matter. And then my second term, which is this group down here, I put in OR, because we started off with ORs. And again, I say to myself, right, what's the same between these two expressions? What is changing and what therefore doesn't matter? So this term here is not A, B, and C. This term here is not A, B, and not C. I can see that my not A and my B are constant through both. I can see that my C term is the one that's changing. Therefore, it's my C that doesn't matter. So I can write this in a simpler form as not A and B. And that's my final expression. That's it. So this is all simplified down here. And I can't simplify it further than that. That's one of the nice things about the Karnaugh map, is that once I've grouped each term, I know there's no simpler way of writing that. But just to give you an example, let me show you how to do the green one as well. It's exactly the same. And remember, while the output will be written differently, logically, it's exactly the same. So depending on your different inputs, it will give the same logical output as this. So once again, I will start with, usually I'll start with my biggest group when I'm doing Karnaugh map groupings, and my biggest group is this vertical group here. So once again, I'm looking at those two terms there, saying what's the same, what's changing, what doesn't matter. This term here is A, B, and not C. This term here is not A, B, and not C. What I can see, it's pretty obvious because it's vertical, is that my A is changing to a not A, therefore it's the A that doesn't matter. So that group there corresponds to B and not C. But now I've got these two groups here. And when you have a single group, what that means is that it corresponds to one whole term with three letters like we started out with. So this one here is the same as A, not B, not C. That term there is not A, B, and C. Okay? So we can see two different expressions. This one is simpler because we had less groupings to start off with. So you can see that in the slides, kind of working through it step by step. You can see both answers there, the simpler one on the left and the more complicated one on the right. Okay. So let's try a different expression now. There's an example. And once we've populated our Karnaugh map, it looks a little bit like this one that I've got here. So let me just update my example on the board so that it matches the one on the slide. Here we go. So now I've got 5 terms, and I've got 1, 1, 1, and 1, 1. By the way, if you're seeing Karnaugh maps, occasionally you'll see people fill in the empty slots with zeros. I leave them blank. It's saying exactly the same thing. The reason I leave them blank is that I think it's just clearer. The ones are the terms that matter. They're what we need to focus our attention on. So how would we simplify this expression here? Well, one other quirk of this table is that, you know how I was mentioning columns? As you move along them, they change only by one value at a time. They only change one thing. What you notice is that if you go from this column here all the way back to the beginning, that's only one change. And in fact, if you go from the bottom of this table back to the top, that's only one change as well. What that means is that the table wraps round on itself. So my groupings, they're not limited by this edge or the top or bottom edges of the table. So I can do something really clever and note that I've got 2 and 2 and 1. But if I group them around the edges, around there and round there, these 4 ones are all the same, part of the same group, right? Even though it goes off the edge of the table, because it's wrapped around, they're all part of one group. And then this is my second group. So if I'm trying to write my output, now I go, okay, what's my output? Again, I look at my first group, which is the big one, these 4 here, and I say, what is important, what's changing, what's not changing. So this is A and B and C, this is not A and B and C, this is A and not B and C, and this is not A and not B and C. So what you're actually getting at there is that because we've got the vertical, clearly the A's don't matter. And what changes between here and here? Well, B, not B, changes to B. That means that both the A term and the B term are not important in that expression. So this whole group here, and this will happen every time you have a group of 4, simplifies down to one term. In this case, the one term is C. And now to complete my expression, I just need to add a term for this here, which is A, B, and not C. A and B and not C. And I'm done. That's my whole Karnaugh map. So the long and short of it is the bigger your groups are, the fewer letters your output expression will have, and the number of groups corresponds to the number of final simplified terms you'll have in your Karnaugh map. So hopefully that explained Karnaugh maps. There's a bunch of other review questions and practice tests and practice questions I've already given you online, but you should be able to simplify an expression using a Karnaugh map. And yes, while you can do it using Boolean algebra, you need to be able to show me that you know how to draw a Karnaugh map and how to use them. You should then be able to take that and draw the logic circuit for that, and then using truth tables for a kind of challenging question, you should be able to verify that your answers are correct. So in summary for this entire lecture, you should know how to sketch logic circuits, you should know what a Karnaugh map is and how to use it, and you should know how to simplify a logical expression using Karnaugh maps. Alright, we'll finish that one there. Hopefully that's pretty clear now.